So hello everyone, welcome back to our another stereochemistry lecture, and this is a lecture 12 of optical activity, and this particular lecture will be very much important in terms of exam point of view and in terms of the people who are doing research in stereochemistry or asymmetric synthesis. This chapter will be very beneficial and very much important for them. Okay, so without further any ado, let's begin with our discussion. So first of all, from the class 1 and class 3 itself, I am actually talking about that the chiral molecule are those molecules who are rotate plane polarized light in either clockwise or anti-clockwise direction. So how to determine the particular optical activity, how to determine the rotation of plane polarized light by using polarimeter. So here in this particular picture or the diagram, you will see the version of polarimeter. Okay, so first is the light source, and in the light source we are getting the light that are not completely polarized, because the electromagnetic radiation here that can be present in any kind of direction. Now this light can be passed through a polarizer, and then it will become a linear polarized light. Okay, and here this is called the sample cell, and the sample cell contain the chiral molecule with the solvent, which are basically achiral. The solvent are basically achiral, so the rotation observed the plane polarized light is mainly due to the chiral substance present in the sample cell. Okay, so this particular polarized light can be passed through this particular chiral solution, and there the deflection can be recorded by using degrees, and here is a detector, and the detector says that how much deflection can be observed during this particular chiral sample, and here we are getting the necessary data for the same. Okay, now if any chiral compound can rotate the plane polarized light either clockwise direction, then we can say it is a dextrorotatory molecule, and if the plane polarized light deflected in the anti-clockwise manner while interacting with the chiral compound, then we are called it is a leviorotatory compounds. Okay, now we are moving about a very important topic regarding optical activity. There is a specific rotation. Specific rotation of a molecule is measured the degree which a chiral molecule can rotate the plane polarized light, and it is used to determine the purity and concentration of this compound in a solution. So the specific rotation alpha that I already discussed, and the specific rotation is a measure of the degree of which chiral molecule can rotate. Now the specific rotation can be defined by the simple formula, that is the alpha SP equal to alpha divided by LC, where alpha is a specific rotation usually expressed in degrees, and the alpha, this alpha is called the observed rotation measured using a polarimeter, and L is the path length of the sample cell, and it is in decimeters. It's a very important. Like normally, whatever we are doing calculations, we are basically using either centimeter as a unit or meter as a unit. But here in the optical rotation calculation, we are use the path length as a decimeter unit. So very important this. And the C is the concentration of the solution in grams per millimeter. There is a gram per ml. Now I want to emphasize a little bit about the alpha SP and alpha. Now alpha SP is observed when the particular compound is present in the full concentration, and alpha, and if the chiral compound getting segregated mixture, like mixture of same enantiomer but in the R form or S form, then depending upon their concentration, the rotation value little bit of changed, and this is be determined by this alpha, and this particular specific rotation is temperature and wavelength dependent. Like if any molecule can show specific rotation of x amount of degrees in 20 degrees centigrade, then it will be different while we measure the same amount of concentration, same amount of chiral compound in 25 degrees centigrade. And similarly, if we change the light wavelength, the alpha specific is also changed. Okay, now we are talking about a little bit of a problem to determine that how can we calculate the specific rotation of the particular compound. So we are dealing with a simple problem. So the question suggests that 28 mg of mandelic acid was dissolved in 1 centimeter cube of ethanol So ethanol is our solvent here, and mandelic acid is our chiral molecule. Okay. Now the solution is placed in 10 centimeter long polarimeter cell. Okay. The cell length is given, means the path length or cell length is given 10 centimeter, and given the alpha of 4.35, optical rotation of alpha 4 was measured at 20 degrees centigrade with a light of 589 nanometers. So temperature and the light wavelength is already determined or given. So what is the specific rotation of the acid? So we have to determine this particular alpha SP. So first tabulated that what the data given. That alpha given is 4.35 degree. Okay. And the concentration is 28 mg per centimeter cube. So we have to change to gram per centimeter cube. So 28 milligram per centimeter cube is 0.028 gram per centimeter cube. And also we have to change the path length. Like path length given here is a 10 centimeter. So we have to change this in decimeter. So decimeter is 1 decimeter. So now we have all the things is there. So we are determining the specific rotation. There is alpha SP. Okay, so alpha SP is defined by the formula. It is alpha SP equal to alpha by LC. So putting all the values, so we get the mandelic acid specific rotation is 155.4 degree. So I hope it will be clear. Okay, now we are talking about very important thing, that is the racemic mixture and racemization. So racemic mixture is an equal mixture of two enantiomer in a chiral center of a chiral molecule. This 1:1 ratio resulted in no net optical activity because the optical rotation of the enantiomer cancel each other out. Example, SN1 reaction. So what actually this statement means? The statement means is in SN1 reaction, both the isomers can be observed because the transition state is something like this. So there is a carbon center and three different groups are there. Okay, now nucleophile, whatever the nucleophile is there, it can be attacked from here also, and it can be attacked from here also. Now the both attack have equal probability. So that's why the both stereoisomers are formed in the same amount, like 50% R form and 50% S product is formed. So what happened that imagine the R product are shown the dextrorotatory rotation of plane polarized light, and the S compound are actually shown the leviorotatory rotation of a plane polarized light. So if the both compound of same if the same structures, both the enantiomers are present in the particular solution, so what happened that these two will cancel each other's plane polarized light rotation, and the makes the solution achiral. How achiral? Because since the both optical rotation are cancelled out each other, so there will be no net plane polarized light rotation observed in the particular detector, and this type of mixture is called racemic mixture. And another important thing is racemization. Racemization is a process by which an optically active compound of one enantiomer is converted into a racemic mixture. This is a very important thing, and this can occur via various mechanism. Okay, so the process of racemization is thermal racemization, base catalyzed, acid catalyzed, and free radical racemization. Now imagine in the our first class we are talking about the thalidomide disaster, and I actually put a statement there that the thalidomide, R thalidomide, we are using for the as a drug. Now this R thalidomide can be converted to racemic mixture or S thalidomide in our body, mainly the thermal process or the process or the kind of bio enzymes are actually working. So these particular things are called racemization. Like we have one enantiomer, there are enantiomer, and this particular enantiomer with some kind of either external factors, it will be converted to a its alternative conformer. There is a S conformer and makes a racemic mixture. And this particular thing is called racemization. Now we are talking about very important thing. There is the enantiometric axis, and mostly this type of question can was come reportedly in the examination itself, like how to determine the enantiometric axis of the particular compound. Now, first of all, talking about the definition, like enantiometric axis is a measure of the purity of a chiral compound representing a different percentage between the two and enantiomer is a mixture, and it is also known as optical purity of the particular compound. Now, how to calculate this enantiometric axis? The formula is enantiometric axis is major enantiomer minus minor enantiomer divided by major enantiomer plus minor enantiomer into 100%. And enantiometric axis has been determined by percent as a value of percent. Okay, and also enantiometric axis can be determined by this particular formula also, where alpha we know that the optical rotation and alpha sp is the specific rotation into 100%. Now let us simplify this with a simple example. Like if your solution contains 70% of one enantiomer R and 30% of the other enantiomer S, then the enantiometric axis is E equal to major minus minor and major plus minor into 100% is 40% enantiometric axis here. Okay, now we are talking about the enantiometric ratio, and this is another important thing. Enantiometric ratio gives the amount of each enantiomer in a mixture. Okay, like enantiomer ratio is usually expected by RS or SR. An example is for a mixture with 70% R and 30% S, the enantiometric ratio is 7:3. Now, just understand the difference between the enantiometric axis and enantiometric ratio. Here, same mixture contain 70% or the same solution contains 70% of one enantiomer and 30% of the other enantiomer. So what happened? The enantiometric axis is 40%. What that 40% is signifies that the rest 60% are form a racemic mixture, because see here, 70% of one enantiomer R is there and 30% of the other enantiomer S is there. So what happened that this 30% of S enantiomer or whatever the enantiomer which present the minor concentration or minor amount, so it will do form a racemic mixture with the major one. Like, so what happened that 70% of one enantiomer is there and 30% of the other enantiomer is there. So the 30% of R out of from the 70%, so 30% of R enantiomer are for racemic mixture of with the S enantiomer. So the resultant optical activity that we are observed is due to this particular 40% of pure R enantiomer. Okay. Similarly, enantiometric ratio tells about the ratio between the R compound and the S enantiomer. So simple, like if the particular mixture or solution contains 70% R and 30% S, the enantiometric ratio is 7:3. Now, similarly, there is a concept of diastereomeric ratio. Diastereomeric ratio is a ratio of amount of each diastereomer in the mixture, similar of enantiometric ratio. And diastereomeric ratio is typically given as dr major diastereomer and ratio of minor diastereomer. Example: if a mixture contains 80% of diastereomer A and 20% of another diastereomer, so diastereometric ratio is 80:20 or 4:1. So I hope this particular lecture is clear to you. And in this particular lecture, we are talking about the optical activity, polarimeter, a little brief, and we are talking about the specific rotation, racemization, and racemic mixtures. And we are talking about the enantiometric axis, enantiometric ratio, and diastereomeric ratio. So in the next particular lecture, we are talking about that how can we resolute the chiral compound. That means from the mixture, can we extract the particular one isomer or one enantiomer from the particular mixture. So with this, I have to end this particular lecture. So thank you for listening.